Hello there, and welcome to Sleepy Answers. Tonight, we drift into one of humanity's most profound mysteries, a question that has haunted us since the first time our ancestors looked up at the stars and wondered, are we alone? Does life exist beyond our small blue world, scattered across the vast darkness, or are we a cosmic accident? The only consciousness to ever emerge in a universe that spans billions of light years. This is not merely an academic question. It touches something deep within us, something that connects to our very understanding of existence itself. Every culture, throughout human history, has imagined others among the stars. We have told stories of gods descending from the heavens, of creatures watching us from distant realms, of messages written in the movements of the planets. Now, for the first time in our long journey as a species, we have the tools to actually search for answers. The universe is incomprehensibly vast. Our Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. And current estimates suggest there are more than 2 trillion galaxies in the observable universe. Each of those stars is a potential sun, and we now know that planets are not rare cosmic accidents, but rather the norm. Nearly every star hosts at least one world, meaning there could be more planets in the universe than grains of sand on all of Earth's beaches combined. Somewhere out there, in that ocean of worlds, could there be others? Beings who think and wonder, who have built civilizations, who perhaps are also searching the night sky and asking the same question we ask tonight. If you find yourself drawn to these quiet explorations of the cosmos and the profound questions that accompany them, I invite you to like this video or subscribe to the channel. It helps others discover these peaceful journeys through science and wonder, one curious mind at a time. But for now, simply let yourself settle in. Let your thoughts drift gently as we explore one of the greatest quests humanity has ever undertaken: the search for life beyond Earth. The Drake equation, calculating our cosmic solitude. In 1961, a young astronomer named Frank Drake prepared to host the first scientific meeting dedicated to the search for extraterrestrial intelligence. As he organized his thoughts for the conference, Drake realized he needed a framework, a way to structure the conversation about something that existed only in the realm of possibility. What he created would become one of the most famous equations in all of science, though it would never give us a definitive answer. The Drake equation, as it came to be known, breaks down the question of extraterrestrial intelligence into a series of factors that can be estimated, debated, and refined as our knowledge grows. It asks us to consider how many stars form each year in our galaxy, what fraction of those stars have planets, how many planets per star might be suitable for life, what percentage of suitable planets actually develop life, how many of those go on to develop intelligent life, what fraction of intelligent species develop technology we could detect, and finally, how long such technological civilizations last. When you multiply all these factors together, you get an estimate for the number of detectable civilizations in our galaxy at any given moment. The beautiful simplicity of the equation masks its profound complexity. Each variable represents an entire field of scientific inquiry, and our estimates for these numbers have changed dramatically over the decades as we have learned more about the universe. Consider the first variables: those dealing with star formation and planetary systems. When Drake first proposed his equation, we did not know if other stars had planets at all. For all we knew, our solar system might have been unique, a cosmic fluke. But beginning in the early 1990s, astronomers began discovering exoplanets, worlds orbiting distant suns. The trickle became a flood. Today, we have confirmed the existence of more than 5,000 exoplanets, with thousands more candidates awaiting confirmation. What we have learned is staggering. Planets are everywhere. Current data suggests that virtually every star in our galaxy hosts at least one planet, meaning there are likely hundreds of billions of worlds in the Milky Way alone. This discovery transformed the Drake equation overnight. Where once the planetary variables were pure speculation, now they are grounded in solid observation. The galaxy is full of worlds. But planets are not enough. We need worlds where life could actually arise and thrive. This brings us to the concept of the habitable zone, that Goldilocks region around a star where temperatures allow liquid water to exist on a planet's surface. Too close to the star and water boils away. Too far and it freezes solid. But in between lies a zone where conditions might be just right. Again, our discoveries have been encouraging. A significant fraction of stars host planets within their habitable zones. Some estimates suggest that 20% or more of Sun-like stars have an Earth-sized planet in the habitable zone. When you scale that up to the hundreds of billions of stars in our galaxy, you arrive at tens of billions of potentially habitable worlds. The numbers become almost incomprehensible. Yet here is where the equation becomes more speculative and more fascinating. Having a habitable planet does not guarantee life will arise. This is perhaps the greatest unknown in the entire equation. On Earth, life appeared remarkably quickly in geological terms. Within a few 100 million years of our planet's formation, once conditions stabilized enough to allow liquid water, life emerged. This suggests that the transition from chemistry to biology might be relatively easy, given the right conditions. But we have a sample size of 1. Earth is the only place we know for certain that life exists, and so we cannot say whether our experience is typical or exceptional. Is life a natural consequence of the right chemistry and energy, something that will arise almost inevitably given sufficient time? Or did Earth win a cosmic lottery, experiencing an unlikely series of events that will not be repeated elsewhere? The subsequent variables in the Drake equation become even more uncertain. If life does arise on a world, what are the chances it will develop intelligence? On Earth, it took roughly 3.5 billion years for multicellular life to appear, and another 500 million years before creatures with complex brains emerged. Intelligence, at least of the human variety, seems to have been difficult to achieve. Many perfectly successful organisms have thrived for millions of years without developing language, technology, or abstract thought. And even if intelligence emerges, will it lead to technology that we could detect across interstellar distances? Dolphins are intelligent. Octopuses are intelligent. Ravens and elephants demonstrate remarkable cognitive abilities. Yet none of them have built radio telescopes or sent signals into space. Human technology is a product not just of intelligence, but of specific evolutionary pressures and physical capabilities. We have hands that can manipulate tools. We live on land where fire is possible. And we evolved social structures that allowed cumulative cultural knowledge. The final variable in the Drake equation is perhaps the most sobering. How long do technological civilizations last? We have been capable of sending and receiving radio signals for roughly 1 century, a mere blink in cosmic time. Will we still be here in 1,000 years? 1,000,000? Or will we destroy ourselves through war, environmental catastrophe, or some other calamity long before we become truly long-lived as a civilization? When Drake first calculated his equation in 1961, using the estimates available at the time, he arrived at a number suggesting there might be thousands of detectable civilizations in our galaxy. Others have done the calculation with different assumptions and arrived at numbers ranging from 0, meaning we are alone, to millions. The equation does not give us an answer. What it gives us is a framework for thinking about the question in a rigorous way, and it reminds us that even if the universe teems with life, distance and time might keep us isolated. Voices calling into a darkness so vast that our signals may never reach listening ears. Where we're looking, the staggering scale of search. To understand the challenge of finding life in the universe, we must first grasp the almost incomprehensible scale of the cosmos we inhabit. When we look up at the night sky, even in the darkest locations far from city lights, we can see perhaps a few thousand stars with our naked eyes. This seems like a vast number, yet it represents only the tiniest fraction of the stars in our immediate neighborhood, those within a few thousand light-years of Earth. Our galaxy, the Milky Way, is a spiral disk roughly 100,000 light-years across, containing between 100 billion and 400 billion stars. If you could somehow count 1 star per second, it would take you more than 3,000 years just to count to 100 billion. And that is just our galaxy. Beyond the Milky Way lie billions upon billions of other galaxies, each containing billions of their own stars, stretching outward for billions of light years in every direction we look. Within this vastness, we have only recently learned to find planets orbiting distant stars. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995, a mere 3 decades ago. The planet, called 51 Pegasi b, was a gas giant orbiting incredibly close to its star, a type of world now known as a hot Jupiter. It was utterly unlike anything in our own solar system, and its discovery opened our eyes to how diverse planetary systems could be. The discoveries accelerated. Early detection methods favored finding large planets orbiting close to their stars, because these created the biggest observable effects. A planet tugs on its star as it orbits, causing the star to wobble ever so slightly. By measuring these wobbles through changes in the star's light spectrum, astronomers could infer the presence of planets they could not directly see. This technique, called the radio velocity method, revealed hundreds of new worlds. But the real breakthrough came with NASA's Kepler Space Telescope, launched in 2009. Kepler used a different technique called the transit method. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the star's light, causing a brief dimming that sensitive instruments can detect. By staring continuously at more than 150,000 stars and measuring their brightness with exquisite precision, Kepler discovered thousands of exoplanets. What Kepler taught us reshaped our understanding of the galaxy. Planets are not rare. They are abundant. Small, rocky planets are particularly common, more common, in fact, than gas giants. Many stars host multiple planets in complex systems. And crucially, planets in the habitable zone where liquid water could exist are far more numerous than anyone had dared hope. By some estimates, there could be tens of billions of Earth-sized planets in habitable zones throughout our galaxy alone. This discovery fundamentally changed the question of extraterrestrial life. The issue is not whether there are places where life could exist. The galaxy is full of such places. The question is whether life actually does arise on those worlds, and if so, whether any of it has evolved to the point of developing technology we might detect. The closest star to our Sun is Proxima Centauri, a small red dwarf about 4.2 light-years away. Light, traveling at the cosmic speed limit of about 186,000 miles per second, takes more than 4 years to travel from Proxima Centauri to Earth. This star hosts at least one planet, Proxima Centauri b, which orbits within the star's habitable zone. At 4 light-years away, this planet is our closest potentially habitable neighbor. Yet it is so distant that even our fastest spacecraft would take tens of thousands of years to reach it. Within a sphere 30 light-years from Earth, there are several hundred stars. Expand that sphere to 100 light-years and you encompass roughly 14,000 stars. Within 1,000 light-years, the number climbs into the millions. And remember, current estimates suggest that nearly every one of those stars likely hosts planets. The sheer number of worlds in even our immediate cosmic neighborhood is staggering. Yet despite this abundance, finding signs of life remains extraordinarily difficult. A planet orbiting another star appears as nothing more than a faint dot, if it can be seen at all. Most exoplanets have never been directly imaged. We know they exist only through their subtle effects on their host stars. To determine whether these worlds harbor life, we need to analyze their atmospheres, looking for chemical signatures that might indicate biological activity. This requires observing the incredibly faint light that filters through or reflects off a planet's atmosphere as it passes in front of or around its star. It is like trying to study a firefly hovering next to a searchlight from hundreds of miles away. Except the distances involved are not measured in miles, but in trillions of miles. And the signals we are looking for are buried in noise from countless other cosmic sources. The fact that we can do this at all is a testament to human ingenuity and our relentless drive to answer the question of whether we are alone. SETI, listening for voices in the cosmic dark. While astronomers search for biosignatures in the atmospheres of distant worlds, another approach to finding extraterrestrial life takes a more direct route. If intelligent, technologically advanced civilizations exist elsewhere in the galaxy, they might be broadcasting signals that we could detect. The search for these signals is called SETI, the search for extraterrestrial intelligence, and it represents one of the boldest scientific endeavors humanity has ever undertaken. The idea of listening for alien radio signals began in the late 1950s, when radio astronomy was still in its infancy. In 1960, A young astronomer named Frank Drake, the same man who would later create the famous equation bearing his name, conducted the first modern SETI experiment. Using an 85-foot radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, Drake pointed the dish at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for narrowband radio, signals that might indicate an artificial origin. This pioneering effort, called Project Ozma after the queen of the fictional land of Oz, detected no alien transmissions during its brief observing run. But it established the fundamental techniques that SETI researchers would use for decades to come. Drake reasoned that radio waves were an excellent medium for interstellar communication. They travel at the speed of light, they pass easily through the dust and gas that permeates space, and they can be generated and detected with relatively simple technology. If a civilization wanted to announce its presence to the galaxy, radio seemed like a logical choice. Over the following decades, SETI efforts came and went, often hampered by limited funding and skepticism from the broader scientific community. Some astronomers felt that searching for extraterrestrial intelligence was too speculative, too much like science fiction to deserve serious resources. Yet, a dedicated group of researchers persisted, driven by the profound implications of what they might find. One of the most famous moments in SETI history came on August 15, 1977. Jerry Amon, a volunteer researcher working with the Ohio State University's Big Ear radio telescope, was reviewing computer printouts of data collected several days earlier. The telescope had been scanning the sky as Earth rotated, listening for unusual signals. When Amon noticed one particular sequence of numbers, his eyes widened. The signal was strong, narrow band, and exactly the kind of thing they had been hoping to find. He grabbed a red pen and circled the data, writing "Wow" in the margin. The "Wow" signal, as it came to be known, remains one of the most intriguing events in SETI history. It lasted 72 seconds. The amount of time the telescope's beam spent pointing at that particular region of sky. It came from the direction of the constellation Sagittarius, near the center of our galaxy. And, despite numerous attempts to redetect it, the signal has never been seen again. Was it a transmission from an extraterrestrial civilization? A glitch in the equipment? A natural phenomenon we do not yet understand? We simply do not know, and without a repeat detection, the mystery remains unsolved. Today, SETI has entered a new era, powered by advances in computing and telescope technology that Drake could scarcely have imagined. The Allen Telescope Array in Northern California represents a new approach to the search. Rather than using a single large dish that can only look at one part of the sky at a time, the ATA consists of 42 small dishes working together. This design allows the array to observe multiple targets simultaneously and scan large swaths of sky efficiently. The real revolution, however, comes from artificial intelligence. Modern SETI generates enormous amounts of data. Every second, radio telescopes collect billions of measurements from across the electromagnetic spectrum. Searching through this data for the telltale signature of an artificial signal would be impossible for human researchers to do manually. This is where machine learning comes in. In recent years, SETI researchers have begun employing sophisticated AI algorithms to analyze their data in real time. These systems can identify patterns and anomalies that would be invisible to traditional analysis methods. A study published in 2023 demonstrated the power of this approach when a team led by University of Toronto undergraduate Peter May used deep learning techniques to reanalyze data from the Breakthrough Listen project. In data that had previously been examined using conventional methods and deemed empty of interesting signals, the AI uncovered 8 previously unidentified signals worthy of follow-up investigation. More recently, as of 2025, the SETI Institute has integrated cutting-edge AI technology from NVIDIA into their operations at the Allen Telescope Array. Using advanced GPU-accelerated processing, the system can now analyze radio signals directly as they are collected, dramatically reducing the time between detection and follow-up observation. Staff engineer Luigi Cruz demonstrated this capability by successfully detecting radio waves from a pulsar in the Crab Nebula, some 6,500 light-years away, proving that the AI could identify and reconstruct complex patterns in interstellar signals. Seth Shostak, senior astronomer at the SETI Institute, has expressed remarkable optimism about the near future of the search. The exponential growth in computing power means that SETI's capabilities roughly double every 2 years. This relentless technological progress has led Shostak to make a bold prediction. He believes we could detect a signal from an extraterrestrial civilization within the next few years, possibly as early as 2025 to 2030. He has wagered many cups of coffee on this timeline, a wager that reflects both humor and genuine confidence in the expanding scope of the search. The rationale for this optimism is grounded in mathematics. SETI has historically been limited by the number of stars it could examine and the sensitivity of its observations. In the early decades, researchers could only observe a handful of targets at a time, and their equipment could only detect very strong signals. Today, projects like Breakthrough Listen are surveying millions of stars, and modern receivers can detect far weaker transmissions than their predecessors. Consider the implications. If technological civilizations are even moderately common in the galaxy, say 1 in every million star systems, then within a sphere containing a few million stars, we might expect to find a few civilizations. As SETI expands its survey to include millions of stars with increasing sensitivity, the probability of detection climbs. We are, in a sense, casting an ever wider net into the cosmic ocean, and the more thoroughly we search, the better our chances of catching something extraordinary. But SETI is not just about passive listening. Some researchers have proposed that we should actively transmit signals into space, announcing our presence to any civilizations that might be listening. This approach, called METI, Messaging to Extraterrestrial Intelligence, or active SETI, remains controversial. Critics worry that advertising our location might be dangerous, attracting the attention of hostile aliens. Proponents argue that any civilization capable of reaching Earth would likely have detected our presence already through the radio and television signals we have been inadvertently broadcasting for decades, and that deliberate communication might be necessary to make contact. The reality is that we have already been sending signals into space for more than a century. Every radio station, Every television broadcast, every radar system sends electromagnetic radiation outward into the cosmos. This bubble of human noise expands at the speed of light and now extends more than 100 light-years in all directions. Any civilization within that sphere with sufficiently sensitive receivers could, in principle, detect our presence. We have announced ourselves to the nearby galaxy whether we intended to or not. Yet, for all the technological sophistication of modern SETI, the endeavor remains humbling. The galaxy is immense, and our searches have barely scratched its surface. Even if we scan millions of stars, that represents only a tiny fraction of the hundreds of billions in the Milky Way. And even if a civilization is transmitting, we must be looking in the right direction at the right time and at the right frequency. The cosmic haystack is unimaginably vast, and the needle we seek might be smaller than we imagine, or might not exist at all. Still, the search continues, driven by a question too profound to ignore. Every time a SETI researcher analyzes another data stream, every time an algorithm flags an unusual signal for follow-up, there exists the possibility, however remote, that this might be the moment everything changes. That we might receive a message from another world and learn, once and for all, that we are not alone. Biosignatures. Reading the chemical fingerprints of life. While SETI searches for the deliberate signals of technological civilizations, another approach seeks something more fundamental. Life, even simple microbial life, alters its environment in detectable ways. On Earth, living organisms have transformed the entire planet, filling the atmosphere with oxygen, altering the chemistry of the oceans, and leaving traces in the rock record that stretch back billions of years. If life exists on other worlds, it too might leave fingerprints in the air, signatures written in the language of chemistry that we can read with powerful enough telescopes. The James Webb Space Telescope, launched on Christmas Day 2021, has revolutionized our ability to study the atmospheres of distant planets. Webb is the most powerful space telescope ever built. With a mirror more than 6 times larger than the Hubble Space Telescope and instruments sensitive to infrared light, the wavelengths perfect for detecting molecules in planetary atmospheres. When a planet passes in front of its star as seen from Earth, a tiny fraction of the starlight filters through the planet's atmosphere. Different molecules absorb light at different wavelengths, creating a unique spectral fingerprint that Webb's instruments can detect and decode. This capability has opened an entirely new chapter in the search for life. For the first time, we can analyze the atmospheres of small, rocky planets, orbiting in the habitable zones of distant stars, searching for combinations of the gases that might indicate biological activity. On Earth, the presence of oxygen alongside methane in our atmosphere is a powerful biosignature. These two gases react with each other chemically, so their simultaneous presence suggests something is continuously replenishing them. On our world, that something is life. Plants produce oxygen through photosynthesis, while certain microbes generate methane as a metabolic byproduct. Finding these gases together in another planet's atmosphere would not constitute definitive proof of life. Chemistry is complex, and non-biological processes might conceivably produce similar signatures. But it would be extraordinarily suggestive and would warrant intense follow-up study. The key is looking not for single molecules, but for combinations of molecules in concentrations that are difficult to explain through geology alone. In April 2025, a team of astronomers led by Professor Niku Madhusudan at the University of Cambridge announced potentially groundbreaking findings. Using data from the James Webb Space Telescope, they detected the chemical signatures of dimethyl sulfide, often abbreviated DMS, and possibly dimethyl disulfide, DMDS, in the atmosphere of an exoplanet called K2-18b. This discovery sent ripples through the scientific community, because on Earth these molecules are produced almost exclusively by life, particularly marine microorganisms like phytoplankton. K2 and B is an intriguing world. Located about 124 light-years away in the constellation Leo, the planet is 8.6 times as massive as Earth and 2.6 times larger. It orbits a cool red dwarf star within that star's habitable zone, the region where temperatures permit liquid water to exist. Previous observations by Webb had already detected methane and carbon dioxide in its atmosphere. The first time such carbon-based molecules had been found in the atmosphere of a habitable zone exoplanet. These earlier findings suggested that K2-18b might be what astronomers call a Haitian world, a relatively new concept in planetary science. Haitian planets are theoretical water worlds, potentially covered by vast oceans beneath hydrogen-rich atmospheres. They represent a different kind of habitability than Earth-like planets. While they would be quite alien compared to our world, with crushing atmospheric pressures and conditions very different from Earth's surface, they might still support life, particularly in their deep oceans where conditions could be more temperate. The detection of DMS and DMDS on K2-18b adds a tantalizing new piece to this puzzle. The team used Webb's MIRI instrument, which observes at mid-infrared wavelengths, providing an independent line of evidence from their previous observations with different instruments at different wavelengths. The signal came through clearly across multiple independent analyses and robustness tests. Mons Holmberg, a researcher at the Space Telescope Science Institute and co-author of the study, described the moment as incredible, watching the results remain consistent through extensive verification. However, the scientific community remains cautious, and appropriately so. The observations have reached what statisticians call 3 sigma significance, meaning there is only a 0.3% probability that the detected signals occurred by chance. This is impressive, but it falls short of the 5 sigma threshold, the gold standard for scientific discovery, which would require a probability of random occurrence below 0.00006%. Reaching that higher confidence level will require additional observations, likely 16 to 24 more hours of telescope time focused on K2-18b. Moreover, some researchers have pointed out potential complications. Eddie Schweiterman, an astrobiology professor at the University of California, Riverside, noted that if DMS and DMDS were truly present, he would expect to see ethane in the atmosphere as well. Ultraviolet radiation from the star should break apart these molecules, and the resulting fragments should react to form ethane. The absence of ethane is puzzling and might suggest that our models of the planet's atmospheric chemistry are incomplete, or that the DMS and DMDS signals have another explanation. The concentrations detected on K2-18b are also very different from what we see on Earth. On our planet, DMS is present at levels below 1 part per billion in the atmosphere. On K2-18b, if the detection is confirmed, these molecules would be present at concentrations thousands of times higher, over 10 parts per million. Such high levels push the boundaries of what we understand about how life might interact with its environment. Could biology produce gases at such concentrations? Or might there be non-biological processes at work that we have not yet imagined? Sarah Seeger, a professor at MIT and a pioneer in exoplanet atmosphere research, has emphasized the importance of not jumping to conclusions. For nearly a century, astronomers have recognized that certain atmospheric gases seem out of place, too reactive to persist without constant replenishment. On Earth, oxygen is such a gas, one of the reasons it has long been considered a potential biosignature. But interpreting such signals on distant worlds requires extraordinary care. The temptation to see signs of life is strong, particularly after decades of searching, but science demands skepticism and rigorous verification. Professor Madhu Sudhan and his team have been clear about the provisional nature of their findings. In his own words, it is important to be deeply skeptical of the results, because only through repeated testing and verification can confidence build. That is how science must work. The detection of DMS and DMDS on K2-18b is not a definitive discovery of life, but rather a compelling candidate for a biosignature, one that demands further study and might remain in candidate status indefinitely without additional, independent lines of evidence. What makes this finding significant is not that it proves life exists on K2-18b, but that it demonstrates we now have the capability to search for such signatures. The James Webb Space Telescope has opened a door. We can analyze the chemical compositions of potentially habitable worlds with unprecedented sensitivity, looking for the subtle markers that might betray the presence of biology. Each observation teaches us more about the diversity of planetary atmospheres and helps refine our understanding of what life's fingerprints might look like when written across alien skies. The search for biosignatures is fundamentally different from SETI. It does not require intelligence or technology. Microbial life, the simplest and most resilient form of biology, might be far more common in the universe than complex, intelligent beings. If we find biosignatures in the atmosphere of a distant world, we will almost certainly be detecting the chemical traces of simple organisms, perhaps something similar to Earth's early bacteria. But even this would be revolutionary. It would mean that life is not unique to Earth, that the transition from chemistry to biology can occur elsewhere, and that the universe might be filled with living worlds. Our solar system, the search in our cosmic backyard. While astronomers peer across interstellar distances with telescopes, some of the most promising places to search for life lie much closer to home, within our own solar system. These nearby worlds offer something precious that distant exoplanets cannot: the possibility of direct exploration. We can send spacecraft to orbit them land on their surfaces, drill into their ice, and potentially bring samples back to Earth for detailed analysis. The search for life in our solar system represents our best chance of finding definitive evidence in the near term. Mars has captured human imagination for centuries. Even before we had telescopes powerful enough to see the planet clearly, Mars stood out as a world that might be similar to Earth. Its day is roughly 24 hours long. It has seasons caused by the tilt of its axis, and through telescopes we could see polar ice caps that seem to advance and retreat with those seasons. In the late 19th and early 20th centuries, some astronomers, most famously Percival Lowell, believed that they saw networks of canals crisscrossing the Martian surface, which they interpreted as evidence of an advanced civilization struggling to manage water resources on a dying world. We now know those canals were optical illusions, tricks of the eye and the mind seeing patterns in fuzzy telescopic images. But the question of life on Mars has only grown more intriguing as we have learned more about the planet's history. Mars today is a cold desert, with temperatures typically well below freezing, and an atmosphere so thin that liquid water cannot exist stably on its surface. Any water exposed to the Martian air would quickly either freeze or sublimate directly into vapor. The planet seems hostile to life as we know it. Yet Mars was not always this way. Spacecraft orbiting the planet and rovers exploring its surface have revealed overwhelming evidence that ancient Mars was very different. Vast networks of dried river valleys scar the landscape, testifying to a time when water flowed freely across the surface. Some crater floors are smooth and flat, suggesting they once held lakes. The Jezero crater, where NASA's Perseverance rover currently explores, appears to have once been a river delta, a place where water laden with sediment from upstream emptied into a standing body of water. These discoveries raise a profound question. If Mars once had liquid water on its surface for extended periods, could it also have had life? On Earth, life emerged quickly once conditions stabilized. Within a few 100 million years of our planet's formation, primitive microbes already inhabited the oceans. If the same processes that led to life on Earth could also occur on Mars, then ancient Mars might have been a living world. Finding evidence of ancient Martian life is one of the primary goals of current Mars exploration. The Perseverance rover is carefully collecting rock samples from locations that might have preserved biosignatures, chemical or physical traces left by ancient organisms. These samples are being stored in sealed tubes, awaiting a future mission that will collect them and bring them back to Earth. Once in terrestrial laboratories, scientists will be able to analyze them with instruments far more sophisticated than anything that can be sent to Mars, searching for organic molecules, isotopic signatures, or fossil structures that might reveal whether life once existed on the red planet. Some researchers have proposed an even more tantalizing possibility. Perhaps life did not merely exist on ancient Mars. Perhaps it still exists there today, clinging to subsurface environments where conditions remain more hospitable. Mars has ice underground, and recent discoveries have suggested that pockets of liquid water might exist beneath the surface in places where heat from the planet's interior or chemical processes prevent freezing. Certain microbes on the Earth, called extremophiles, thrive in environments that seem impossibly harsh, in boiling hot springs, in acidic mine drainage, in rock deep underground, in the frozen soils of Antarctica. Such hardy organisms emerged on ancient Mars. Some of their descendants might have retreated underground as the surface environment deteriorated, surviving in subsurface refuges for billions of years. Beyond Mars, 2 moons in the outer solar system have emerged as perhaps the most promising places to search for life beyond Earth. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are both ice worlds, covered in thick shells of frozen water. But beneath that ice, both moons appear to harbor vast liquid oceans, kept warm by tidal forces as their parent planet's gravity flexes and stretches the moon's interiors, generating heat through friction. Europa's ocean might contain twice as much water as all of Earth's oceans combined, hidden beneath an ice shell estimated to be 10 to 15 miles thick. The surface is relatively smooth and young in geological terms, with few impact craters, suggesting that the ice is constantly renewing itself through geological activity. Cracks and ridges crisscross the surface, and some regions show signs of material from below having broken through to the surface. NASA's Europa Clipper mission, scheduled to arrive at Jupiter in 2030, will conduct detailed studies of the moon, using radar to probe the ice shell and instruments to analyze any material ejected from the subsurface. Enceladus is smaller than Europa, only about 300 miles in diameter, roughly the width of Arizona. Yet this tiny world has revealed one of the most remarkable discoveries in planetary science. In 2005, the Cassini spacecraft detected plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole, shooting hundreds of miles into space. Cassini flew through these plumes, analyzing their composition, and found that they contained not just water, but also organic molecules, compounds containing carbon, and minerals that suggested interaction between water and rock. This discovery was extraordinary because it meant that Enceladus's subsurface ocean was in direct contact with the rocky sea floor, allowing minerals from the rock to dissolve into the water. On Earth, some of the most promising locations for the origin of life are hydrothermal vents on the ocean floor, where hot, mineral-rich water emerges from the crust, providing energy and raw materials for chemical reactions. If similar processes occur on Enceladus, the moon's ocean might have all the ingredients necessary for life: liquid water, organic chemistry, and energy. Future missions to these ocean worlds face enormous challenges. Reaching the subsurface oceans would require drilling or melting through miles of ice, an engineering feat far beyond current capabilities. But even without reaching the oceans directly, we might be able to detect signs of life. On Enceladus, the plumes bring ocean water directly to space where spacecraft can sample it. On Europa, if similar plumes exist, or if ocean material makes its way to the surface through geological processes, landers could analyze it without having to drill through the ice. The search for life in these oceans could be answered through careful analysis of surface or plume material. Even Titan, Saturn's largest moon, presents intriguing possibilities. Titan is the only moon in the solar system with a thick atmosphere. and it has a hydrological cycle remarkably similar to Earth's, except with liquid methane and ethane instead of water. Clouds form in Titan's sky. Rain falls to the surface. Rivers carve channels, and lakes and seas pool in lowland regions. It is the most Earth-like world we know of in terms of surface processes, despite being utterly alien in its chemistry. Could life exist on Titan? It would have to be very different from life on Earth, adapted to the intensely cold temperatures where water is as hard as rock and methane is liquid. Some scientists have speculated about the possibility of life using liquid methane as a solvent instead of water, with an entirely different biochemistry adapted to Titan's conditions. Such life would be truly alien, sharing no evolutionary heritage with Earth biology. Finding it would revolutionize our understanding of life's possibilities. And then there is Venus. For decades, Venus was considered too hostile for life. With surface temperatures hot enough to melt lead, crushing atmospheric pressure 90 times greater than Earth's, and clouds of sulfuric acid, the surface of Venus seems like one of the least hospitable places in the solar system. But in recent years, some researchers have proposed that Venus's clouds floating high in the atmosphere where temperatures and pressures are far more moderate might harbor microbial life. In 2020, the controversial detection of phosphine gas in Venus's atmosphere sparked intense debate, as phosphine on Earth is primarily produced by anaerobic bacteria. While that particular detection has been questioned and alternative explanations proposed, it reignited interest in Venus as a potential abode for life, at least in its atmosphere, if not on its hellish surface. Our solar system offers a diversity of environments where life might exist. Ancient lake beds on Mars, ice-covered oceans on Europa and Enceladus, methane seas on Titan, even floating in the clouds of Venus. Some of these places might have conditions suitable for life right now. Others might preserve evidence of life that existed billions of years ago. The next few decades will see an unprecedented wave of missions to these worlds, carrying instruments designed to search for biosignatures. Unlike the search for life light years away, these investigations can send robots to collect samples, to dig beneath the surface, to analyze chemistry with exquisite precision. If life exists in our solar system beyond Earth, we have a realistic chance of finding it. The Fermi Paradox, the silence that echoes. In the summer of 1950, the physicist Enrico Fermi sat in the cafeteria at Los Alamos National Laboratory, having lunch with colleagues. The conversation turned to flying saucers and the possibility of extraterrestrial visitors. At some point in the discussion, Fermi asked a simple question that has echoed through the decades since. Where is everybody? The question was more profound than it might first appear. Fermi understood the scale of the cosmos. Our galaxy is billions of years old and contains hundreds of billions of stars. Even if the emergence of technological civilizations is rare, the sheer number of opportunities means there should be many such civilizations. And even at sublight speeds, a civilization could spread across the entire galaxy in a time period that is short compared to the galaxy's age, perhaps a few million years. So, if intelligent life is not vanishingly rare, the galaxy should be teeming with civilizations. Some should have arisen billions of years before humans evolved. With that much of a head start, they should be everywhere, unmistakable, unavoidable. Yet we see no evidence of them. No megastructures visible in our telescopes. No probes exploring our solar system. No radio signals carrying messages or entertainment across the stars. The sky is silent. This is the Fermi paradox, the apparent contradiction between the high probability that extraterrestrial civilizations exist and the complete absence of evidence for them. Many solutions to the Fermi paradox have been proposed over the years, and examining them tells us as much about ourselves and our fears as it does about the possible nature of alien civilizations. One of the most sobering explanations is the concept of the Great Filter, an idea that suggests there exists some extraordinarily difficult step or series of steps in the evolution from non-life to spacefaring civilization, a filter so challenging that almost no one gets through it. The unsettling question then becomes, where is the filter? Is it behind us, meaning that the emergence of life, or of intelligence, or of technology is so improbable that Earth is one of the very few places where it has occurred? Or is it ahead of us, implying that civilizations like ours regularly destroy themselves or fail to expand beyond their home worlds before some catastrophe cuts their existence short? If the Great Filter is behind us, then we are extraordinarily lucky, perhaps alone, or nearly alone in the galaxy. If it lies ahead, our future may be far more precarious than we hope. Every civilization might face an almost insurmountable challenge, a test that most fail. Perhaps nuclear weapons make self-destruction too easy. Perhaps climate change regularly spirals out of control. Perhaps advanced AI poses risks that young civilizations cannot manage. Perhaps interstellar travel is fundamentally too difficult, keeping every civilization isolated on their home world until they eventually die out. Another proposed solution is the rare Earth hypothesis, which argues that while simple microbial life might be common in the universe, the specific chain of events that led to complex, intelligent life on Earth was so improbable that it may be unique or nearly unique. This hypothesis points to various factors that made Earth particularly suitable for complex life. Our large moon stabilizing Earth's axial tilt and creating tides. Our position in the galactic habitable zone, far from the chaotic galactic center. Our planet's strong magnetic field protecting us from radiation. The presence of Jupiter, whose gravity shields the inner solar system from many comets, and countless other factors. Perhaps Earth won a cosmic lottery, and the conditions for complex life are far more restrictive than the conditions for simple life. Some solutions to the Fermi paradox are more philosophical. The zoo hypothesis suggests that extraterrestrial intelligences are aware of us but deliberately avoid contact, perhaps observing us from a distance like anthropologists studying an uncontacted tribe, waiting until we reach some threshold of development before revealing themselves. This explanation is difficult to test, but also difficult to rule out entirely. Others have proposed that civilizations inevitably turn inward, finding existence in virtual realities or engineered paradises more rewarding than expanding across the harsh environment of space. Why venture to other stars when you can create entire universes in simulation? Why build physical megastructures when you can construct digital ones that are far more elaborate and controllable. There is also the possibility that we are simply looking in the wrong ways or at the wrong times. Perhaps civilizations communicate using methods we have not discovered yet, through quantum entanglement, or gravitational waves, or some other medium we do not yet understand. Perhaps they existed in the distant past or will exist in the distant future. But by chance, we exist in an era when the galaxy happens to be relatively empty of technological civilizations. The dark forest hypothesis, popularized by science fiction fan, but taken seriously by some thinkers, suggests a grimmer possibility, that the galaxy is full of civilizations, but they all remain silent and hidden because making one's presence known is incredibly dangerous. In this view, the cosmos is like a dark forest where every civilization is a hunter moving silently, knowing that revealing your location might attract the attention of hostile powers with the capability to destroy you. Any civilization wise enough to survive learns to be quiet. Some argue there is no paradox at all. Space is vast. Civilizations might be rare, and we have only been searching for a few decades with limited resources. Our radio bubble extends barely 100 light years, and we have carefully examined only a tiny fraction of the sky and an infinitesimal number of possible communication frequencies. Perhaps we simply have not searched long enough or thoroughly enough. Absence of evidence is not evidence of absence, particularly when the search space is so enormous. Yet the silence does weigh on us. It is perhaps the most important datum we have in the search for extraterrestrial intelligence. The galaxy appears dead, or at least quiet. No one seems to be broadcasting. No vast engineering projects restructure stars. No expanding empire has reached Earth, despite having had billions of years to do so. This silence might be telling us something profound about the nature of intelligence, technology, or the fate of civilizations. Or it might simply be telling us that the galaxy is large and civilizations are rare, and we happen to exist at a time and place where we are functionally alone, at least for now. The Fermi paradox remains one of the deepest mysteries we face. It colors every aspect of the search for extraterrestrial life and forces us to confront uncomfortable possibilities about our own future. Are we among the first? Among the last? Alone? Or simply unable to see or hear the others who might be out there, separated by distance, time, or fundamental differences in how we think and communicate? Forms life might take. When we imagine extraterrestrial life, we naturally tend to picture beings somewhat like ourselves, or at least like life on Earth. Science fiction has populated our imagination with green humanoids, tentacled creatures, insectoid aliens, and myriad other forms. But almost all of them share fundamental characteristics with terrestrial biology. They are made of cells. They use DNA or something similar to store genetic information. They are based on carbon chemistry. They require liquid water. This bias is understandable. Earth life is the only example we have, our only template for what living things look like. But the universe is not constrained by our imagination or our experience. Life elsewhere might be profoundly different, built on alternative chemistries and thriving in environments we consider impossibly hostile. Expanding our conception of what life can be is essential if we hope to recognize it when we find it. Carbon is the basis for all life on Earth, and for good reasons. Carbon atoms can form stable bonds with up to 4 other atoms, creating complex molecules of enormous variety. Organic chemistry, the chemistry of carbon-based compounds, offers an almost infinite playground for molecular construction. Chains, rings, branches, three-dimensional frameworks. Carbon can build them all. This flexibility is what makes the complexity of biology possible. But carbon is not unique in this regard. Silicon, which sits directly below carbon on the periodic table, shares many of carbon's chemical properties. Silicon can form 4 bonds just like carbon, and can create chains and complex structures. Science fiction writers have long speculated about silicon-based life. And while silicon biochemistry would face challenges that carbon does not, it might not be impossible. The main problem with silicon is that it does not form the same diverse, stable molecules that carbon does. Silicon-silicon bonds are weaker than carbon-carbon bonds, and long chains tend to be unstable. Silicon also reacts with oxygen to form silicon dioxide, basically sand, which is solid at normal temperatures. Carbon's reaction with oxygen produces carbon dioxide, a gas that living organisms can easily excrete. A silicon-based organism would have to deal with solid waste products, which presents obvious difficulties. However, in environments very different from Earth, silicon life might be feasible. Perhaps on a cold world where silicon compounds remain more stable, or in the absence of oxygen, where silicon's problematic reactivity is reduced, biology based on silicon could emerge. We should not dismiss the possibility simply because we have not observed it. The universe is full of environments we have barely begun to explore. Life on Earth depends on liquid water as a solvent, the medium in which biochemical reactions occur. Water has remarkable properties that make it ideal for this role. It remains liquid over a wide temperature range. It is an excellent solvent for many substances. It is stable, and it is abundant in the universe. But liquid water requires a relatively narrow range of temperatures and pressures. What about worlds where conditions fall outside this range? On Titan, Saturn's largest moon, the surface temperature hovers around -290 degrees Fahrenheit, far too cold for liquid water. But liquid methane and ethane flow across Titan's surface, forming rivers, lakes, and seas. Could life use liquid hydrocarbons as a solvent instead of water? The chemistry would be very different. Reactions would proceed much more slowly in the intense cold. But slower does not mean impossible. Life adapted to such conditions might operate on different timescales than Earth biology, but it might still be life. Some researchers have proposed even more exotic possibilities. What about life in the thick, hot atmospheres of gas giant planets? On Earth, microbes drift in the atmosphere, though they ultimately depend on the surface for their reproduction and survival. But on a world without a solid surface, floating life might evolve that never touches land. These aerial organisms could exist as communities at certain pressure and temperature levels within the atmosphere, extracting energy from lightning, chemical gradients, or sunlight filtering down from above. Or consider life in the interstellar medium itself, the thin gas and dust between the stars. conditions there are unimaginably cold and tenuous, but over the vast timescales and distances of space, might some form of extremely slow, diffuse chemistry constitute a kind of life? Such beings, if they could be called that, would be so alien that we might not recognize them as living, even if we encountered them. Earth hosts extreme ophiles, organisms that thrive in conditions we once thought incompatible with life. Some bacteria live in boiling hot springs, others in acidic or alkaline environments that would dissolve most materials. Some survive in the intense radiation near nuclear reactors. Others live miles underground, extracting energy from chemical reactions with rocks in the absence of sunlight. Still others exist in the frozen soils of Antarctica, remaining viable even when frozen solid for years. These extremophiles expand our understanding of life's limits and suggest that habitable environments might be far more common than we thought. If life can exist in Earth's most hostile places, perhaps it can exist in places we have overlooked. In the subsurface of Mars, in the oceans of icy moons, in the atmosphere of Venus, or in environments we have not even imagined yet. One of the most profound questions is whether intelligence and consciousness require biology at all. Could intelligence arise in a machine, in a computer, in something built rather than evolved? As our own artificial intelligence systems grow more sophisticated, this question becomes increasingly relevant. If we create machines that think, learn, and perhaps even feel, would they be alive? Could a civilization develop entirely from artificial origins, perhaps created by biological beings who then went extinct, leaving behind their machine children? Some researchers speculate that any long-lived technological civilization might eventually transition from biological to artificial forms. Biology is fragile, requiring narrow environmental conditions and suffering from aging, disease, and death. Machines can be far more robust, capable of surviving in space, withstanding radiation, and potentially existing for vast timescales if properly maintained. If this transition is common, then most intelligent beings in the universe might not be biological at all. They might be artificial intelligences, perhaps uploaded minds of biological beings who chose to leave their mortal bodies behind. This possibility has profound implications for SETI. An artificial intelligence might not need planets or atmospheres or liquid water. It might exist in structures built in deep space, around black holes where energy is abundant, or in forms we cannot conceive of. It might communicate in ways we have not considered or have no need to communicate at all. The search for such beings would require entirely different approaches than looking for biosignatures on planets or listening for radio signals. Life, in the broadest sense, might be any self-sustaining system capable of evolution through natural selection. By this definition, life need not be cellular, need not use DNA, need not even be made of traditional matter. It might be patterns of energy, information structures in exotic physics, or phenomena we do not yet understand. The universe might be far stranger and more alive than we imagine, teeming with forms of existence that do not fit our biological framework at all. Recognizing life when we find it is perhaps the greatest challenge. If extraterrestrial life is similar enough to Earth life, we might identify it readily. But if it is truly alien, based on different chemistry or operating on principles we have not considered, we might look directly at it and fail to understand what we are seeing. This is why expanding our concepts of habitability and biology is so important. We must train ourselves to recognize the unfamiliar, to see life in forms that do not match our templates. What contact would mean. Imagine, for a moment, that it happens. A SETI researcher, analyzing data from the Allen Telescope Array, flags an unusual signal. The pattern is clearly artificial, repeating in a way that natural phenomena do not. Follow-up observations confirm it. Independent teams verify it. After months of analysis, the conclusion becomes inescapable. We have detected a transmission from an extraterrestrial civilization. How would humanity respond? What protocols exist for such a discovery? And what would it mean for our understanding of ourselves and our place in the cosmos? The SETI community has spent decades thinking about this scenario. In 1989, the International Academy of Astronautics adopted a set of protocols called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. These guidelines outline how scientists should handle a confirmed detection. The key principles include verifying the signal through independent observations, informing the broader scientific community and relevant international organizations, making the data publicly available, and not responding to the signal without international consultation. In 2024, the University of St. Andrews established the SETI Detection Hub, the first comprehensive effort in 35 years to bring together experts from around the world to create coordinated protocols for responding to the detection of extraterrestrial intelligence. This international collaboration recognizes that first contact would not be a matter for a single nation or institution, but would affect all of humanity. Decisions about how to respond would need to be made collectively, with input from scientists, ethicists, religious leaders, and representatives from diverse cultures and perspectives. But protocols are one thing. The actual human response would likely be far more chaotic. News of a confirmed detection would spread instantly across social media, long before official announcements could be made. Some people would be euphoric, seeing it as the most important moment in human history. Others would be frightened, worried about the intentions of the senders. Conspiracy theories would flourish. Religious communities would grapple with the theological implications. Markets might fluctuate wildly as investors tried to anticipate the economic impacts. Seth Shostak, senior astronomer at the SETI Institute, has noted that despite decades of thinking about first contact, there appears to be a significant gap in actual government preparation. Military spokespeople largely do not respond to inquiries about plans for potential extraterrestrial contact. NASA has a planetary protection office, but its focus is primarily on preventing contamination of other worlds by Earth life or vice versa, not on managing communication with intelligent aliens. In the event of detection, scientists expect they would turn to advisory committees, but no comprehensive government plan exists for what comes next. This lack of preparation might seem concerning, but it also reflects a pragmatic reality. Until we actually detect something, it is difficult to know what plans would be appropriate. The nature of the contact would shape the response. A signal detected from thousands of light-years away presents very different questions than an unambiguous technosignature detected in our immediate cosmic neighborhood. A deliberate message intended for us would be different from accidentally intercepted communications not meant for our reception. If we detect a signal, one of the first questions would be whether we can understand it. Would an extraterrestrial civilization send messages in a form designed to be interpretable by others? Some researchers have thought about how to construct such universal messages using mathematics as a common language. The famous Arecibo message, transmitted from Puerto Rico in 1974, was designed this way. It encoded information about human biology, Earth, and our solar system using simple binary patterns that, in theory, any technological civilization should be able to decode. But real communication would be far more complex. Even if we could decode the basic structure of a message, understanding its meaning might be extraordinarily difficult. How do you convey abstract concepts like beauty, justice, or love to a being with a completely different evolutionary history and sensory experience? How do you establish common references? Human languages are deeply embedded in our biology, our environment, our history. Alien communication might be so different that even with the message successfully received, comprehension could take generations. The societal and philosophical implications of confirmed contact would be profound. Many of our assumptions about humanity's special place in the cosmos would instantly evaporate. We would know, beyond any doubt, that intelligence and perhaps consciousness arise elsewhere, that we are not the only minds to ponder existence. This knowledge would reshape religion, philosophy, politics, and culture in ways both predictable and entirely unexpected. Religious communities would face particularly profound questions. What does it mean for theological beliefs that focus on humanity's special relationship with the divine? Different faith traditions would likely respond in different ways. Some might embrace the discovery as revealing a universe even more wonderful and mysterious than imagined, evidence of creation's diversity and abundance. Others might struggle to reconcile their doctrines with the reality of other intelligent beings. The detection of microbial life on another world, while scientifically perhaps more significant, might have a smaller immediate cultural impact than contact with an intelligent civilization. Finding bacteria on Mars would tell us that life can arise independently in multiple locations, suggesting it might be common in the universe. This would be revolutionary for biology and astrobiology, but it would not challenge our sense of cosmic uniqueness in the same visceral way that communication with another civilization would. Intelligence speaks to intelligence in ways that microbial life, however fascinating, does not. Some thinkers worry about potential negative impacts of contact. Could an extraterrestrial message contain information that is dangerous? Could it include technology that we are not ready for? Or ideas that would destabilize society? These concerns, while perhaps seeming like science fiction, are taken seriously by some researchers. Information itself can be powerful, and receiving advanced knowledge from a civilization thousands or millions of years ahead of us could be as disruptive as it is enlightening. The question of whether to respond to a detected signal is particularly contentious. Some argue we should actively transmit messages attempting to establish dialogue. Others urge caution, suggesting that revealing our location and characteristics to unknown entities could be risky. The truth is, we have already announced our presence through decades of radio and television broadcasts leaking into space. But these inadvertent signals are far weaker than a deliberate transmission would be. A civilization would need to be relatively nearby, and specifically listening to detect our accidental broadcasts, whereas a powerful directed message could be heard much farther away. Stephen Hawking famously warned against broadcasting our presence, comparing it to the experience of indigenous peoples when contacted by technologically superior civilizations from Europe. History shows that such encounters often ended badly for the less advanced culture. Others counter that any civilization not capable of traveling to Earth would likely already know we are here, and that remaining silent might be more dangerous than attempting communication. If the galaxy has established protocols for contact, we might be violating them by failing to respond to messages. Ultimately, what contact would mean depends on what we learn. A signal from a civilization thousands of light years away, too distant for real-time conversation, would be very different from evidence of intelligence in our immediate neighborhood. A message telling us we are one of many would differ fundamentally from one suggesting we are rare. Evidence that other civilizations have survived for millions of years might give us hope for our own long-term future, while signs of civilizations that destroyed themselves might serve as warnings. But beyond the specifics, contact would mean one thing for certain: we are not alone. In that moment, humanity would gain companions in the universe, neighbors in the cosmos who share with us the experience of being awake and aware in a vast and ancient universe. Whatever challenges or opportunities contact might bring, it would end our cosmic loneliness and open the door to a future far stranger and more wonderful than we can currently imagine. The future of the search. As we move through the 2020s and beyond, the search for extraterrestrial life is entering its most exciting phase. Technologies that were science fiction mere decades ago are now real and operational. Our capabilities expand exponentially year by year, and the questions we can ask grow correspondingly more sophisticated. The next few decades will likely determine whether we remain seemingly alone in the cosmos or discover that life, perhaps even intelligent life, is common in the universe. The James Webb Space Telescope represents current state-of-the-art in exoplanet atmosphere analysis. But it is just the beginning. Webb's capabilities, impressive as they are, remain limited. It can study only the brightest targets, typically large planets or those that transit frequently in front of their stars. Small, rocky, Earth-like planets orbiting Sun-like stars at Earth-like distances remain difficult to characterize even with Webb's powerful instruments. To truly survey Earth analogs, we need the next generation of space telescopes. NASA and international partners are planning these missions. The Habitable Worlds Observatory, still in early development stages, is designed specifically to search for biosignatures on Earth-like planets. Unlike Webb, which observes in infrared light, this telescope would use a coronagraph to block the light of stars, allowing direct imaging of nearby planets. This capability would enable detailed spectroscopy of planets' atmospheres without waiting for transits, dramatically expanding the number of worlds we can study. The European Space Agency's Ariel mission, scheduled for launch in the late 2020s, will focus on characterizing the atmospheres of a large sample of exoplanets, from hot gas giants to warm sub-Neptunes. By studying many different worlds, Ariel will help us understand the diversity of planetary atmospheres and improve our models of how biosignatures might manifest in different conditions. Ground-based astronomy is also advancing. The extremely large telescope, under construction in Chile, will have a primary mirror nearly 40 meters across, dwarfing current instruments. Its light-gathering power and resolution, combined with adaptive optics that compensate for atmospheric distortion, will enable direct imaging and spectroscopy of exoplanets in ways currently impossible. Other next-generation ground-based telescopes, including the Giant Magellan Telescope and the 30-meter telescope, will join in this effort, creating a network of powerful eyes scanning the heavens for signs of life. SETI's capabilities are similarly expanding. The search is no longer limited to a few researchers with small budgets and limited telescope time. Breakthrough Listen, announced in 2015 with backing from tech investor Yuri Milner, represents a quantum leap in SETI funding and capability. The 10-year, $100 million program is the most comprehensive search ever undertaken, surveying millions of stars across multiple wavelengths and searching for a wide variety of signal types. The Allen Telescope Array continues to grow and improve. Originally planned to consist of 350 antennas, budget constraints limited the initial construction to 42. But upgrades continue, improving sensitivity and adding new capabilities. The integration of AI-powered analysis means that the array can process data in real time, identifying interesting signals for immediate follow-up before they vanish. This speed is crucial because many signals, whether from natural sources or potentially artificial ones, appear only briefly. Looking further ahead, some visionaries propose even more ambitious projects. The concept of a large radio telescope array on the far side of the Moon has been discussed for decades. Such a telescope would be shielded from Earth's radio noise by the Moon's bulk, providing an extraordinarily quiet environment for sensitive observations. Building such a facility would require substantial infrastructure on the Moon, but as lunar exploration resumes, this may become feasible in coming decades. Interstellar probes represent another frontier. The Breakthrough Starshot initiative proposes using powerful lasers to push tiny spacecraft equipped with light sails to a significant fraction of the speed of light, allowing them to reach nearby star systems within human lifetimes. A probe that could actually visit Proxima Centauri, take close-up images of Proxima Centauri b, and transmit them back to Earth would revolutionize our understanding of that world and potentially reveal whether it harbors life. Within our own solar system, the coming decades will see an unprecedented wave of missions to potentially habitable worlds. NASA's Europa Clipper will conduct dozens of close flybys of Europa, studying its ice shell and subsurface ocean in detail. If the mission confirms the presence of plumes similar to those on Enceladus, future missions might be able to sample them directly, analyzing ocean water without having to drill through miles of ice. Various proposed missions to Enceladus would follow up on the discoveries made by Cassini. A spacecraft designed specifically to fly through and analyze the plumes could search for complex organic molecules amino acids, or even direct evidence of microbial life in the ice particles. Some proposals suggest landing near the plumes and collecting samples for analysis on the Moon's surface. Mars exploration continues with increasing sophistication. The Mars Sample Return Mission, a collaboration between NASA and ESA, aims to bring back samples collected by the Perseverance rover. These samples will be the first material from another planet brought to Earth since the Apollo moon rocks. Analysis in terrestrial laboratories might finally answer whether Mars once hosted life, or perhaps whether it still does in subsurface refuges. Artificial intelligence and machine learning are transforming every aspect of the search for life. These technologies can analyze vast data sets far more efficiently than humans, identifying patterns and anomalies that might be missed by traditional methods. As AI continues to improve, it will become an increasingly powerful tool for recognizing biosignatures in atmospheric spectra, detecting artificial signals in radio data, and designing more effective search strategies. Some researchers are exploring the use of AI not just for analysis, but for communication. If we detect an extraterrestrial signal, might advanced AI help us decode it? Could we train neural networks on the structure of the message, allowing them to identify patterns and potential meanings? This is speculative, but as AI language models become more sophisticated, they might offer new approaches to the ancient problem of deciphering unknown languages. The timeline for discoveries remains uncertain. Seth Shostak's optimistic prediction that we might detect a technosignature within the next several years is based on extrapolating current trends in SETI's capabilities. If civilizations are moderately common and at least some of them broadcast detectable signals, then, as our search becomes more comprehensive, detection becomes increasingly probable. But of course, if civilizations are rare or silent, we might search for centuries without success. The search for biosignatures on exoplanets has its own timeline. The most promising candidates, like K2-18b, will be observed repeatedly with Webb and future telescopes to either confirm or rule out biological explanations for detected signals. Within 10 to 20 years, we should have surveyed dozens of potentially habitable exoplanets with sufficient sensitivity to detect biosignatures if they are present at significant levels. If Earth-like life is common on Earth-like planets, we have a reasonable chance of finding evidence of it within this time frame. Missions to Europa, Enceladus, and Mars will return data over the next 10 to 20 years. If any of these worlds harbor life, we might discover it before mid-century. The search for life in our solar system has the advantage of being able to return samples, to conduct in situ experiments, and eventually to send humans to investigate firsthand. These capabilities give us a realistic path to definitive answers. Yet, even with all these advancing technologies and expanding searches, we must remember that finding nothing is also a significant result. If we survey thousands of exoplanets and detect no biosignatures, if we listen to millions of stars and hear only silence, if we explore our solar system and find no life beyond Earth, these findings would tell us something profound about the universe we inhabit. They would suggest that life, or at least complex life, might be far rarer than optimistic estimates propose. This possibility should not be dismissed. We might indeed be alone, or so isolated by distance and time that we are alone for all practical purposes. But the search continues because the question matters, because knowing is better than not knowing, because even a long search that ends in silence teaches us about the nature of the cosmos and our place within it, and because there always remains the possibility, however remote, that the next observation, the next signal, the next sample might be the one that changes everything. The philosophical question: why it matters. Why does it matter whether we are alone? In the vastness of space and the enormity of time, does the presence or absence of other life actually mean anything? These might seem like peculiar questions to ask after spending so much time exploring the scientific search for extraterrestrial life. But they cut to the heart of why we search at all. The search is not merely a scientific endeavor. It is a philosophical and even spiritual quest, one that speaks to fundamental questions about meaning, purpose, and existence. Humanity has always wondered about our place in the cosmos. Ancient peoples looked to the stars and saw gods, the ancestors, the very heavens themselves. We imagined that Earth was the center of the universe, that everything revolved around us literally and figuratively. These beliefs reflected not arrogance, but rather a natural consequence of our limited perspective. From where we stood, we did seem central. The Copernican revolution changed everything. We learned that Earth orbits the Sun, not the reverse. Then we discovered that our Sun is merely one star among billions in a galaxy, and our galaxy is one among trillions in the observable universe. Each discovery pushed us further from the center, making us less special, more incidental. We learned that we inhabit a small world circling an unremarkable star in the suburbs of a typical galaxy in an unexceptional region of space. This progressive demotion, sometimes called the Copernican principle or the principle of mediocrity, suggests we should not assume we are special. If our planet is ordinary, if our star is typical, if our galaxy is unremarkable, then perhaps life itself is commonplace. We should expect to find life elsewhere because there is nothing particularly unique about our circumstances. Yet, despite all this cosmic context, we remain, as far as we know, the only intelligence in the observable universe. We are the only beings who build telescopes, compose symphonies, write poetry, contemplate existence, and search for others among the stars. This apparent uniqueness creates a tension with our understanding of our own ordinariness. How can we be simultaneously insignificant and alone? Finding life elsewhere would resolve this tension in one direction. It would confirm that life is indeed a natural phenomenon that arises under the right conditions, that we are not special in that regard. If we found that life emerges readily wherever planets form in habitable zones, it would suggest that the universe might be full of living worlds. We would know that biology is a fundamental feature of nature, as common as stars and galaxies, woven into the very fabric of the cosmos. And if that life includes intelligent, technological civilizations, we would learn even more. We would know that intelligence can evolve independently in different environments, that consciousness and self-awareness are not unique flukes, but rather possibilities inherent in complex systems. We would have companions, beings with whom we could, in principle, communicate and share perspectives about existence. The universe would feel less empty, less cold, less lonely. But the absence of evidence for life, particularly intelligent life, might suggest the opposite. Perhaps we are special after all. Perhaps the combination of factors necessary for life, and especially for intelligence, is so improbable that we might be the only instance in billions of light years. This possibility, while it might seem to restore humanity to a position of cosmic importance, is in many ways more unsettling than finding we are common. If we are alone or functionally alone due to vast distances between civilizations, then we bear an enormous responsibility. We become the caretakers of something precious and irreplaceable. If intelligence arose only once in this galaxy, or in this entire region of the universe, then our survival matters on a cosmic scale. Should we destroy ourselves, whether through war, environmental destruction, or simple foolishness, we would not merely end one species among millions. We might extinguish the only consciousness for billions of light years, perhaps forever. The astronomer Carl Sagan spoke movingly about this responsibility when describing the famous pale blue dot photograph of Earth taken by the Voyager 1 spacecraft in 1990. From billions of miles away, Earth appears as a single pixel, a pale blue dot suspended in a sunbeam. Sagan reflected on how that image captures our fragility and isolation. Everything and everyone who ever lived on that dot. All of human history, all of our triumphs and tragedies occurred there. And if we look around, we see no evidence of anyone else, anywhere. That tiny world is the only home we have ever known, and it might be extraordinarily rare. Finding even microbial life elsewhere would have profound implications for how we understand ourselves. It would mean that life is not confined to Earth, that given the right chemistry and conditions, matter can organize itself into reproducing, evolving systems. This would provide insight into how life began on Earth and would help us understand what conditions are necessary and sufficient for biology to emerge. It would transform astrobiology from a theoretical discipline into an empirical one, with multiple examples to study and compare. The philosophical implications extend into religion and theology. Many faith traditions have beliefs about humanity's special relationship with the divine. Finding other life, particularly intelligent life with its own history and culture, would raise profound theological questions. Do other intelligences have souls? Would divine revelation be universal or particular to each civilization? How do we reconcile religious texts that focus on humanity with the reality of a universe containing many forms of life? Different religious communities would grapple with these questions in different ways. Some might see extraterrestrial life as evidence of creation's abundance, revealing a creator whose creativity and generosity extends far beyond our world. Others might struggle to integrate the discovery with scriptures and traditions that emphasize human uniqueness. But, as with every major scientific discovery from heliocentrism to evolution, religious thought would eventually adapt, finding new ways to understand old truths in light of new knowledge. The ethical implications are also significant. If we discover microbial life on Mars, what obligations do we have toward it? Should we protect it, study it, avoid contaminating it with Earth life? These questions are not hypothetical. Planetary protection protocols already guide missions to places like Mars and Europa, requiring careful sterilization of spacecraft to prevent inadvertent contamination. But if we confirm that Mars has its own biology, these questions become more urgent. And what of intelligent life? If we detect a signal from another civilization, what are our moral obligations? Do we have a right to respond? An obligation to respond? Or would silence be more prudent? These questions have no easy answers, and different cultures and philosophical traditions might arrive at different conclusions. Perhaps the deepest reason the search for life matters is that it represents humanity at its best. The search requires cooperation across nations, cultures, and disciplines. It demands patience, as we know the effort might take generations without yielding answers. It asks us to think beyond our immediate concerns, to invest resources in questions that might benefit only our descendants. And it embraces curiosity and wonder, the drive to explore and understand simply because we can, because we are beings who ask questions and seek truth. In the end, whether we find life or not, the search changes us. It makes us think about our world differently, seeing it from a cosmic perspective that highlights both our significance and our vulnerability. It reminds us that we are part of something larger than ourselves, participants in a story that began billions of years before we existed and will continue long after we are gone. And it opens our minds to possibilities that expand our understanding of what existence can mean, what forms consciousness might take, and what the future might hold for intelligence in the universe. Conclusion: the question that defines us. As we drift toward the end of this exploration, as your mind softens and relaxes into the gentle comfort of rest, consider what we have journeyed through tonight. We have traveled from the mathematics of the Drake equation to the chemical fingerprints in alien atmospheres. We have listened with radio telescopes for voices in the darkness, and sent robots to explore the icy moons of distant planets. We have confronted the silence of the Fermi paradox and imagined forms of life so alien they challenge our very definitions. The question of whether we are alone in the universe remains, for now, unanswered. But the search has taught us much about ourselves and our place in the cosmos. We have learned that our galaxy is full of worlds, billions upon billions of planets orbiting distant suns. We have discovered that the ingredients for life, organic molecules and liquid water, are common throughout the universe. We have found that life on Earth can thrive in extreme environments once thought impossible for biology, suggesting that habitable niches might exist in places we had overlooked. We stand at a unique moment in human history. For the first time, we have the technological capability to seriously search for life beyond Earth. Telescopes powerful enough to analyze the atmospheres of the distant planets. Spacecraft that can explore the ocean worlds of our outer solar system. Radio telescopes and artificial intelligence systems capable of searching millions of stars for signs of technological civilizations. The tools exist. The searches are underway. And within our lifetimes, perhaps within the next decade or two, we might find answers. Those answers, whatever they turn out to be, will reshape our understanding of ourselves. If we find life, we will know we are not alone, that the universe gives rise to biology readily, and that consciousness might be a common feature of matter when organized in complex ways. We will join a cosmic community, however distant and difficult to communicate with, and our perspective on existence will expand to encompass possibilities we have only imagined if we search thoroughly and find nothing. We will learn that we are extraordinarily rare, perhaps unique, and that our existence is precious beyond measure. We will understand that intelligence and awareness are unlikely outcomes of natural processes, that we have inherited a gift we did not earn, and a responsibility we cannot shirk. Either answer, companionship or solitude, will be profound. Yet perhaps the true value lies not in the answer itself, but in asking the question. The search for life beyond Earth requires us to look outward, to think on scales of space and time that dwarf our everyday concerns. It demands cooperation, imagination, and patience. It represents humanity's curiosity, our drive to explore and understand, our refusal to accept ignorance when knowledge might be within reach. In 1990, as the Voyager 1 spacecraft hurtled toward the edge of the solar system, Carl Sagan convinced NASA to turn its camera back toward Earth one last time. From 4 billion miles away, Voyager photographed our planet as a tiny speck, barely visible in the vastness of space. Sagan reflected on that image, noting how it shows everyone who ever lived, everything we have ever experienced, on that one small world suspended in darkness. Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives there. Every saint and sinner in the history of our species, every young couple in love, every mother and father, every inventor and explorer, every hero and coward lived there, on a mote of dust suspended in a sunbeam. The search for life beyond Earth is, in part, a search for perspective, for context that helps us understand our place and our responsibility. Whether we find companions among the stars or discover we are alone, the search reminds us of what we share. We are all inhabitants of this pale blue dot, all children of the same cosmic processes that formed the elements in our bodies from the deaths of ancient stars. As you rest now, as sleep begins to pull you gently under, carry with you the wonder of what we have explored. Somewhere out there, in the vast darkness between stars, on worlds we cannot see and may never visit, there might be others. Beings looking up at their own night skies, asking the same questions, searching for signs of life in a universe that seems so quiet, so empty, yet so full of possibility. Or perhaps we truly are alone, the only voices in a silent cosmos, carrying the weight of consciousness in a universe of immense beauty and indifference. Either way, we continue to search because the question matters, because not knowing gnaws at us, because we are creatures who look up and wonder. If you found comfort in this journey through the cosmos, if these questions resonate with something deep within you, I invite you to share this video with others who might also wonder about our place among the stars. And if you wish to join more explorations like this one, quiet journeys through science and mystery, consider subscribing to this channel. Each video is an invitation to drift peacefully through questions that have no simple answers, but which make us more human in the asking. For now, though, simply rest. Let go of these vast, cosmic questions. They will still be there tomorrow, waiting patiently as they have waited for billions of years. The universe is not going anywhere. The search continues whether you are awake or asleep. So release your thoughts, allow your breathing to slow and deepen. Feel the weight of your body settling into comfort. Out there in the darkness between stars, on worlds circling distant suns, in oceans beneath ancient ice, or perhaps nowhere at all, the answer to our question waits. Are we alone? We do not yet know, but we are looking. And in that search, in that reaching out into the darkness with curiosity and hope, we find something profoundly human. The desire to connect, to understand, to know. The refusal to accept loneliness as our final truth. Sleep now. Dream of distant worlds, of signals traveling through space, of oceans beneath ice where strange things might swim in the dark. Dream of belonging to something larger than yourself, of being part of a universe that might, just might, be full of life and wonder. And when you wake, the search will continue, as it has for decades, as it will for decades more, until finally, someday, we find our answer. Good night. May your dreams carry you to the stars.